In this video, we're going to take a look at trig identities. Now, in A-level maths, we're going to learn a range of different trig identities. However, for the first year material, which is what we're covering in this video, then we will need to know two trig identities. So let's just give those results to begin with. So the first one here is sine squared theta. So sine squared theta plus cos squared theta is identical to 1. So that's the first result we need. And then the second result is tan theta. So tan theta is identical to sine theta over cos theta. Okay. So now let's show how we prove these results here. So these are results that we need to be familiar with. But what we're also going to show is how we actually derive these results. And the way these results are derived is given from the unit circle. So this is a circle given as x squared plus y squared is equal to 1. So this circle is centered at the origin, 0, 0, and it has a radius of 1. Okay. So the way we get these results is using the unit circle and a basic bit of trigonometry and Pythagoras. So what I'm going to do here is just take this triangle here. So we have this angle of theta, and I've got this base here and this height here. Okay, so let's say I've took this point here, okay, which has coordinates x, y. So we have x, y there. So my base is x units, and my height is y units. Now I've got this angle theta here. So if I label this triangle here, this would be the opposite side. This would be the opposite. I would have a right angle here because clearly the axis here is perpendicular to this side. So in that case, this would be the hypotenuse here across. This would be the hypotenuse. And then clearly this would leave the adjacent here at the base. Okay, so that's my adjacent. So what I'm going to do now is just make use of some basic trigonometry and Pythagoras. So in this case, let's just give the trig ratios here. So using SOHCAHTOA. So using SOHCAHTOA here. Okay, you don't need to write this out, but just to show our ratios here. Then sine. So sine theta is going to be equal to the opposite over the hypotenuse. That's the opposite over the hypotenuse. Cos theta, so cosine of theta, that would be equal to the adjacent over the hypotenuse. The adjacent over the hypotenuse. And then finally, tan theta. So tan theta here is going to be equal to the opposite over the adjacent. Okay, so that's the opposite over the adjacent. So what does this show us here? Well, clearly in this case then, using our triangle here with this unit circle, in that case, sine theta, so sine theta here, that's going to be the opposite over the hypotenuse, so opposite over hypotenuse, which in our case means we've got y over the hypotenuse, which in this case, the hypotenuse must have a length of 1. Okay, that's this radius. So I'm going to have the opposite here, which is y over 1, which is the hypotenuse here. Like we said, the hypotenuse has a length of 1. So in that case, I get y over 1, which is simply y there. Okay. We can do the same here with cos theta. So cos theta, that would be the adjacent over the hypotenuse. So the adjacent is x here over the hypotenuse, which is 1. I get x over 1, which would give me x there. Okay. Now, if we go back to the definition of our unit circle here, x squared plus y squared is equal to 1. In that case then, if I substitute in x equals cos theta and y equals sine theta, then what I'm going to get here is cos squared theta plus sine squared theta is equivalent or identical to 1 here. Okay. And that just comes from this definition here of the unit circle and applying some basic trigonometry. So that's the first result there that we can see here. Clearly it's just written in a slightly different way. It's written as cos squared first, but it does not matter. But we would typically write it like this. So sine squared theta plus cos squared theta is identical to 1. So that's the first result boxed off there. Happy days. And from this now we can see then that tan theta is identical to sine theta over cos theta. Well, in that case, if tan theta is equal to the opposite over the adjacent, then we just go back to this definition here and our triangle that we've drawn from the unit circle here, then the opposite is y over the adjacent, which is x. So I get y over x, which in our case, y over x, that's going to be y here is sine theta. We've got sine theta over x, which we know is cos theta. So x equal to cos theta. And now that's our second result proved there. So therefore, tan theta is identical to sine theta over cos theta. Okay. And like you can see, these results are actually quite easy to prove as long as we use the unit circle like this and apply some basic trigonometry and Pythagoras. Okay, so that's the first result proved there, and that's our second result. Okay. So that shows the derivation of those results. So now let's take a look at a couple of practice questions of using these trig identities. So for the first question here, we're asked to prove that sine to the power of 4x minus cos to the power of 4x is identical to sine squared x minus cos squared x. So let's just note the two identities that we're familiar with here. We know sine squared, in this case x, plus cos squared x is identical to 1. So that's my first identity. So sine squared x plus cos squared x is identical to 1. And then we also know that tan x is identical to sine x over cos x. Now notice here, the way I've denoted these two identities, I've changed theta to x. It doesn't matter. Obviously, we're using x in this question here, so I'm just going to change my identities to match that. Now, we might not need to use both of these identities. We might only need to use one, but I'm going to note them here just so we have them at hand to use here. Okay. So, where do we begin? Well, what you'll find with a lot of these identity questions is you need to be able to spot what's going on with the question and the little tricks associated with these types of questions. So a very common one is using the difference of two squares. And I notice straight away here with this sine to the power of 4x minus cos to the power of 4x, I can apply the difference of two squares there. So I can rewrite this here, this left-hand side, as sine squared x minus cos squared x times sine squared x plus cos squared x. Okay, if we used to expand these two brackets out here, we'd get this left-hand side. So what we're going to do now is take this left-hand side here and see if we can work towards the right-hand side of this identity. So in this case, there's actually not too much more to do here, because if I just take a look at the two identities that we've got here, what I've got now is sine squared x minus cos squared x times sine squared x plus cos squared x. Well, we know sine squared x plus cos squared x is equivalent or identical to 1. So in that case, I just get one lot of sine squared x minus cos squared x, like so. Obviously, if I times through by 1, I just get this right-hand side here, which is equal to sine squared x minus cos squared x. Okay, and there we have it. That's our solution. Like you can see, sometimes it might only take a step or two, like we did there, but it's just spotting that first kind of step there on how to get started. So big clue for a lot of these questions is think of the difference of two squares. It will crop up quite a bit, so it's always something to have there ready at our disposal. So that's the solution to question 1. Let's take a look at one more question now. So what I'm asked to do for this question is to prove that sine squared theta plus 1 plus cos theta all squared is identical to two lots of 1 plus cos theta. So what I'm going to do is I'm going to take the left-hand side of this identity here and then hopefully get it to something that's matching this right-hand side here. Okay. Now to begin with here, what I'm going to do is just denote the two identities that we're already familiar with. So I've got, in this case, because we're working with theta, I've got sine squared theta plus cos squared theta is identical to 1. And I've also got that tan theta identical to sine theta over cos theta. Okay. So I just box these off again here, just so we have them at hand. So what I'm going to do here is take the left-hand side, just rewrite that down here just so we can see it a bit clearer. So sine squared theta plus 1 plus cos theta all squared. And what I want to do is show that we can write that as two lots of 1 plus cos theta. Now, if I take a look at this expression here, the only thing I can actually do here is just to expand this double bracket. So what this is 1 plus cos theta times 1 plus cos theta. Okay, So just expanding using FOIL or any method that you're familiar with here. I'm going to get 1 times 1, so that'll be 1. So if I just rewrite the sine squared out again, so sine squared theta, I'm going to get plus 1. I then do 1 times cos theta, so that would give me cos theta. Then we do cos theta times 1, so I get 2 lots of cos theta there. So we've got plus 2 cos theta. I've then also got cos theta times cos theta, which would give me cos squared theta. So plus cos squared theta. Okay. And that's it. Once we fully expand that, that's what we get there, those 3 terms. Okay. Now from here, we take a look at this and hopefully we can identify an identity that we can use here. And I notice straight away that I've got a sine squared theta and I've got a cos squared theta. So when I add those together, we know that that's identical to 1. So what I'm going to do is I'm just going to put them together. We don't have to do this step here. You can just go straight away to putting this as 1. But I want to just show that once we put those together, it makes it clear that this is the identity that we're using. So I've got sine squared theta plus cos squared theta. I've got plus 1 and then plus 2 cos theta. Okay. So from here now, like we said, this part here, we know that's identical to 1. So what I've got now is 1 plus 2 cos theta. Well, 1 plus 1 is 2, so I've got 2 plus 2 cos theta. And what I can do now is factor this 2 out here, like they've got. So I've got 2 lots of 1 plus cos theta there, okay, which is equal to the right-hand side. And then our proof is complete there, okay. So that's our solution. And like you can see, these questions, usually the trickiest part is just getting started, knowing what the first kind of step is there. Once you kind of get going, everything usually just falls quite nicely into place. But definitely the trickiest part is just getting started. Okay, but there we have it. So that's our solution to question 2. And that brings us to the end of this video on trig identities.